Welcome back to ECE 442-542. In this video, we are going to work with our performance specifications or design specifications to create or build a desired transfer function T sub C, which the C subscript is really referring to closed loop. These are our desired behaviors that we want our controlled system to exhibit. Once we've finished creating this transfer function, which we're calling T sub C, we'll try to validate that using MATLAB. Here's what we want to do. We want to build a transfer function, T sub C of Z, that has two performance specifications satisfied. One of those is we want it to have a peak time of 10 samples and a 1% settling time of 30 samples. And we've said nothing about a particular sample period, and we can actually design poles or desired polynomials without having to specify a unique or a specific value of a sample period, as long as we make the specification in terms of a certain integer number of sample periods. And in this case, the peak time is 10 sample periods long, and the settling time, the 1% settling time, is 30 samples. And this is really the picture that you should be seeing, this graphic of this output response y of n versus time, and you can see that it peaks then for the first time, and we call that T sub p, or the time that it peaks. And then it enters into this 1% tube and stays there. That 1% tube is 1% away from its final value on either side. And when it gets into that tube and never leaves, that's when we call it the settling time, or capital T sub S. And we're going to go ahead and assume that in creating this transfer function, capital T sub C of Z, it's going to be a second order denominator or a second order system. It will have two poles in the denominator to try to satisfy these design specifications. So we're given time to peak in number of samples, and if we wanted to convert those, or if we needed to know what that looked like in absolute time, then we would have to multiply that number of samples by the sample period capital T. But we haven't been given a capital T in this problem, so we can actually solve for these pole locations without being told an explicit value for capital T, although in just a little bit I'll give you a capital T just as an example so that you can start to feel or get some insight into the relationship between peak time and settling time in absolute time sense. The settling time is 30 samples, and here, as I promised, here's our aside. This is not required. This green text is not required for this problem, but I'm providing it to try to help you get some insight or understanding. So in this aside, let's suppose that our sample period in seconds per sample is 0.02 or 20 milliseconds in length. We can immediately find the sampling frequency in hertz by taking the reciprocal of capital T, and that's now 1 over 0.02, or 0.02 is really 2 over 100. That 100 now jumps into the numerator, or can be, by multiplying numerator and denominator by 100. And now we can maybe more easily see that 1 over 0.02 is in fact 50 hertz, or 50 cycles per second. And that's how quickly we are going to be sampling this system, or would, or could. This again is just an aside. And if we wanted to know what is that sampling frequency in radians per second, then that's our sampling frequency in hertz times 2 pi. Or it's 2 pi divided by capital T. The 2's cancel, the 100 pops up, and we now have a sampling frequency of 100 pi radians per second, which if we round pi to 3, it's roughly 300 radians per second, just to give you a feel for the relationships between sample period. You're sampling all waveforms every 20 milliseconds in time. That represents 50 hertz in terms of a sampling frequency, or roughly 300 radians per second. The highest frequency in this sampled system that we will be able to determine or identify is really limited to 1/2 the sampling frequency. And we'll show that maybe in subsequent videos. But here that means that if we're sampling at 50 hertz, the highest frequency that we can actually distinguish in all of the frequencies in our system is 25 hertz, or half of that. Or in terms of radians per second, that's 150 radians per second. Using this aside, using this supposed sample period of 20 milliseconds, or 0.02, the peak time now is 0.2, or 200 milliseconds, and the settling time is 3 times that in this particular problem, and that then represents 600 milliseconds, or 0.6 seconds. So a little bit more than half a second, this system should be settled. That's what we want for this desired sample period and these performance specifications of a peak time of 10 samples and a settling time of 30. Again, that was just to give you something to think about, to hang your hat on, to try to get a feel for what is going on with respect to peak time and settling time. If in fact we were sampling at 50 hertz and we were wanting a settling time of 30 samples, that means that a little bit more than half a second, if we do a constant input into this system within a little bit more than half a second, it will have settled into its final value. Let's go back to building this transfer function, capital T sub c of z, which we said we're going to build it to satisfy these two design specifications using two complex poles, and those desired poles then were giving a magnitude of r, capital R, and an angle of theta sub d. That's the polar form representation of these desired poles. And what we want to do then is use these design specs for peak time and settling time to find values for r and theta sub d. Once we have r and theta sub d, we can then determine this second order polynomial that will be in our denominator of our desired transfer function. We can find r from the settling time. Remember, settling time gives us circles. The 1% settling time we can determine by this relationship, or using the relationship, r raised to the number of sample periods we want to be in our settling time. So now how long does r take to collapse down to 0.01 when we keep raising it to higher and higher powers? And we want that power finally to be, in our case, n sub s of 30 to drive r less than 0.01. We can start to solve this then for r by taking the base 10 log of both sides and then taking the anti-log, and now we have a formula for the radius of our desired poles based on a settling time specification of 30 samples. So we now have r is equal to 10 raised to the minus 2 over 30, or that's the same as just putting that 10 raised to the 2 over 30 in the denominator. And now we have 1 over 10 to the 1/15th. That power is a little bit bigger than 0, so it's a little bit bigger than 1, and we would expect then 1 divided by something bigger than 1 to give us an r value inside the unit circle. We need to be inside the unit circle in order to be talking about a settling time, and in this case our r is 0.8577. we now have half of the information we need to specify our closed loop poles. We can find the other half, the angle, theta sub d, using the peak time design specification or performance spec, and the peak time again are these angles in the z-plane. Peak time, if we derived it from this continuous time second order system that's purely second order, it's now pi divided by omega sub d, where omega sub d in the s-plane is our imaginary distance of the complex poles, or it's the distance we are away from the real line in the s-plane. Recall in the z-plane that we have this angle theta sub d is equal to this damped frequency omega sub d times the sample period capital T, and we can use that now to solve for omega sub d in terms of theta sub d. Again, we're trying to find a formula for theta sub d, the angle in the z-plane. We can now substitute this relationship into the denominator of our peak time formula to find a peak time expression in terms of theta sub d. Or our peak time now is pi over the quantity theta sub d over t. Take that sample period into the numerator, and we now have a peak time formula equaling pi t over theta sub d. Our peak time again was 10 sample periods. We haven't defined what t is. It's just some variable, capital T, in our example here. So our peak time is 10 of those, 10t, but we also know from this formula that the peak time is pi t over theta sub d. We cancel the t's and we have 10 is equal to pi over theta sub d. Solving that for theta sub d says that we need an angle to meet these design specifications of 1/10 of pi, or 0.314159. We don't have to have that many specific or significant figures, but we did. And here we have 0.314 radians per sample for our angle, or if we want to think in terms of degrees, if we're not used to thinking about 30% of a radian, then we can convert that theta sub d into units of degrees, knowing that pi is equivalent to 180 degrees. So we now have 180 divided by 10, or 18 degrees per sample. We now have all that we need to locate these dominant poles in our desired transfer function T sub c of s. And that's going to have a radius of 0.86 roughly, and it's going to be at an angle of 18 degrees. We found the radius from the settling time specification. We found the angle from the peak time. And we can now, if we want, using Euler's our friend, we can now use Euler to take that polar form of these poles into rectangular form. And the real component, which I might label z sub r, is capital R cosine of theta sub d. And the imaginary component, z sub I, is capital R sine of theta sub d. Doing the math, we now end up with z sub d in rectangular form as 0.82 plus and minus, actually. We're going to have its twin, 0.26. That's going to be then the poles. This is now producing the denominator. If you plug in z delta for z in this formula, you will see that the denominator vanishes, either for z delta at the plus imaginary component or the minus imaginary component. Both of those will cause the denominator to vanish. In this case, our T sub c, we're going to go ahead and put a 0 at the origin. That wasn't in our design specifications, but that will give us a pole zero excess of 1, and that now means that we have, because of that pole zero excess of 1, we have 1 sample period delay between when we apply the input and when we see it at the output. So in a sense, that z in the numerator by itself has advanced this relationship that we have in our desired transfer function t sub c of z by 1 sample period. So let me go ahead and say that this is now t sub c of z equaling kz over the desired denominator polynomial that has roots at 0.8157 plus and minus j 0.265. The only remaining unknown in that desired transfer function is this variable gain k, and let's go ahead and select the gain k to produce a DC gain of 1 in this desired transfer function t sub c of z. Our DC gain in the z-plane is found when we evaluate the transfer function when z is equal to 1. And so now you should be envisioning this z-plane plot, and you're now evaluating at z equal to 1. We plug in 1 for z in our t sub c expression, set that equal to 1. That's what we want our DC gain to equal. We only have one unknown in this expression, and we can solve for k just by cross-multiplying the numerator and denominator in that expression with 1, and we end up with a gain k of 0.1042. That now gives us the desired transfer function that we want. Capital T sub c of z is 0.1042 z over this second order denominator. It should have a DC gain of 1, and it should have a peak time of 10 sample periods and a settling time, a 1% settling time of 30 sample periods. That's by design. We want to try to validate that now using MATLAB, and we can do that by entering these two polynomials, the numerator polynomial and the denominator polynomial, into MATLAB. And here is the numerator. We now hopefully see that this row vector is the coefficient 0 is scaling z to the 0, and we just keep moving to the left for higher powers of z. So in this case, the numerator is actually that gain times 1 times z plus 0 times z to the 0. And that's what we wanted. We wanted 0.1042 times z. The denominator we're going to generate the same way. Here, this corresponds to z squared's coefficient. This is the z to the 1 coefficient, and this is the constant in our denominator, which is just the real part squared plus the imaginary part squared, or it's the radial distance away from the origin. It's the hypotenuse in this right triangle defined by the z delta locations. Once we have our numerator and denominator polynomials entered into the MATLAB structure, we can use the TF, the transfer function within MATLAB, to compute the transfer function, which I'm calling on the left T sub c. And in this case, we're telling MATLAB that we are not going to specify a particular value for the sampling period, capital T. And the way that we do that, we need to tell it a sample period because it needs to know that it's a discrete time system. But if we haven't picked, or if we haven't specified a sample period, how do we tell MATLAB that in fact we have a discrete time system in this transfer function? So the way to do that is to say, oh, -1 is our sample period. And that really tells MATLAB, oh, you have no sample period actually selected. or t is unspecified, and now you're going to try to determine everything based on just the number of sample periods. Let's now go into MATLAB and do what we are trying to do, which is validate our desired second order transfer function. The gain, k, was 0.1042, and we're going to use that to scale the polynomial z, which in MATLAB is now going to be corresponding to this vector 1, 0. There's our numerator polynomial. Our denominator polynomial is z squared, and then we have minus 2 times the real component, which was 0.8157, and then we want to go ahead and take the square, and I'm just going to go ahead and multiply those out so that you explicitly see what's going on. So the constant coefficient is going to be the real part squared plus the imaginary part squared. And that's now our denominator polynomial. We can now say, oh, and I think before, didn't I call this TC? So I'll go ahead and call this TC is equal to the transfer function of num denom with no specified sample period. And there is now our transfer function, and if we want to, we can now, in a figure, we can look at the step response of that particular transfer function, second order. I'm waiting for the prompt to come back so that we know that we have now seen, or that the figure has been generated. It's taking a little bit of time, but once we generate this figure, then we'll go on and do a few more things, and hopefully you can see that it is peaking at 10 sample periods, so don't read too much into the label down below. That x-axis really is time in sample periods and not seconds, and you can see that by the time we get out to 30 sample periods, we have pretty much entered into that 1% tube. So let's now look at what would happen, or maybe make MATLAB a little bit more honest with what it's saying is the horizontal axis, by indeed specifying a particular sample period. So let's go ahead and say that we want to now introduce a particular sample period of what we had experimented with before in our aside comment, which was 20 milliseconds, or 0.02. There is now our sample period. Let's now say this is TC1 for a slight variation. It's the transfer function. Same numerator, same denominator. It's just now we have a particular sample period selected. MATLAB tells us that. It says the sample period is 0.02 seconds. We can now, let's open up a second window by just saying figure, and it will produce a second figure window, or a new one. Let's say step of TC1. And now in the second figure window, now you can see that in fact we are peaking at 0.2 seconds, and we're essentially settled at 0.6 seconds, which is what we had said we wanted to achieve with this particular design. Now, in terms of helping you plot things when you might have specifications in terms of radius or damping ratio zeta, or maybe even natural frequency, let's look at what we can actually generate from within MATLAB. We can actually generate a figure that we can print out and use to help us pinpoint locations in the complex z-plane. Here's the z-plane. It looks a little bit distorted, so let's go ahead and make the real and imaginary axis equal so that our angles are actually valid. Now we have a circle, and the logarithmic spirals, which are these heart shapes that I was suggesting before, are labeled as 0.9 as the first one you see closest to the origin, and then they just decrease in zeta value up to 0.1, and then the unit circle is a zeta value of 0. And these other lines are actually perpendicular to these logarithmic spirals, and those correspond to the frequency, and when they're on the unit circle, those are the natural frequency. And in this case, you see the first one from z equal to 1 as you go up in angle is at 1/10 pi over cap t. The biggest sort of frequency that we can have over at -1 is pi over t. And we've now subdivided that 180 degrees up into 10 different angles, so that now at 1/10 pi over t, and we could find the angle, that would just be, the angle is now omega sub n times t on the unit circle, and in this case it would be 0.1 pi over t times t, or 1/10 pi, or 18 degrees. So you can see then that those particular curves, that's the natural frequency. And as we increase the damping, we now have a damped frequency, and this would now correspond to a natural frequency of 0.1 pi over t and a zeta value of 0.9 if we located our pole, the top one, in the first quadrant at where I'm now sort of highlighting with the arrow. And maybe I should expand that so that you can see it a little bit better. But here is an angle. If you now multiplied this omega sub n times t, you would now have 1/10 pi, or 18 degrees, 36 degrees, and you could sort of draw these angles, and those would be your angles corresponding to peak time. But these curves that are perpendicular to the logarithmic spirals, which are the zeta curves, these curves are actually our natural frequency curves corresponding to a particular natural frequency, and they've now been identified or labeled on the unit circle, but those now migrate through as we increase the value of zeta. Now you can use this to sketch or find your dominant poles on this, or you could create even a little bit more particular z-plane grid if you wanted to. You could say, let's say that we just want to have zeta values of 0.3, 0.7, and 0.9 on this grid. And suppose that we want the omega to be 0. Now let's open up a new figure window. We don't want to get rid of the one we just created. Let's go ahead and say our axis is equal so that the angles are all nice, and do a z-grid in terms of z and w. So w is 0, and we have the three zeta values of 0.3, 0.7, and 0.9 labeled, and here is our sort of unit. This is our unit circle with the axis equal, and this is now giving us the opportunity to sketch in this z-plane with those particular grids. Now that might be a little bit challenging to try to sketch, so let's put in some more information, maybe a horizontal line, x going from -1 up to 1, and we don't want to see that in increments of 0.01. Let's go ahead and do a 0 for the y, And now we can hold on to that last figure that we had opened, and we can now plot xy. So now we're plotting y with respect to x. Y is 0, and x is going from -1 to 1. So that should give us a horizontal line going through the origin in our previous figure. And in fact, it does. In this case, it's labeled it, or it's putting it from -1 to 1 through the horizontal line. Now we might want to actually plot a vertical line going through the origin. So let's just say, oh, if we keep our x-coordinate 0, which is what we had for y, and work through the y varying from -1 to 1, which is what x was, I'm now going to plot y and x just the opposite that I did before. So now I should have a vertical line. And now maybe you don't like the blue and the red. You can actually tell MATLAB to pick a different color. So let's now say xy. This is the horizontal line. Let's make it black, which is k. And that now looks good. Let's now plot y comma x black. And now maybe we can see that we like that. Or if you don't, and really we don't need to have both top and bottom shown necessarily to be plotting our complex poles. We really just need to work with half of those, or the upper half, and we can do that if we now restrict our axis to be from x -1 to 1 and y from 0 to 1. So now we're just looking at the top half of that particular graph, and you can see that I entered the command wrong. I forgot to give axis the function a left parenthesis, and maybe instead of retyping that, I can just up arrow, and now it's actually balanced for me, and now I should be able to issue that command without an error. And now you can see that we just have the top half of that Z grid with zeta values of 0.3, 0.7, and 0.9. And obviously you can put whatever values you want, and that gives you an idea as to how to sketch or produce some of these graphs to make your life a little easier when you're trying to locate these complex poles. And we also were able to, by looking at figure 2, verify or validate our design transfer function with a peak time of 0.2 and a 1% settling time of 0.6 in a second order system. And you can see that we do have a 1 sample period delay between when we apply the input at the origin and when we actually see it at the output.